Hi everybody, in this video I'm going to go through one of the exercises in your book and also show you how to use this code lens feature and also go to the original tool for visualizing Python, which I think is just a really awesome tool and is really helpful if you're confused about your code or just want to understand something about Python. So the activity that I wanted to show is in section 8.6. This is part of a reading assignment, and this is activity 2, and here we see a function, newtonSqrt, that computes the approximation of the square root of a number using the accumulator pattern in a while loop. So basically at every step it's improving the approximation. And so you will have seen in reading assignments this code lens feature that allows you to step through the code. I guess I'm actually at the end. Let's go to the beginning. And so first, let's just take a look at what we see as we execute this code using code lens. So the red arrow indicates which line of Python will be executed next, and so we start at the top of the file, line 1, first line with a Python statement in it. And what happens on this line? Well, if we were just running this normally in idle, say, we wouldn't see anything. But in code lens, we get a view into what's going on. So what happens here is that in the global frame, so that's a global frame for our entire program, a variable called newtonSqrt is created, and this variable points to the function that is about to be defined, or that we will go look at if we call newtonSqrt. And we can also see what's going to be executed next. It's actually not anything inside the function because we only execute the code inside the function when it's called. So what's executed next is this line 9. And what does line 9 do? Well, it executes the newtonSqrt function, with n being the variable n being set to 10. So in this second frame here, so this is the newtonSqrt frame, so it's a local frame to the function. The variable n has the value 10. Then on the next two lines, we set the variables approx and the variable better to have specific values, 5 and 3.5. Next, we're going to check this while loop condition. So we're only going to do the things inside the while loop if better is not equal to approx. And let's just try to make a prediction. Should this happen or not? Well, better is 3.5, approx is 5, so yes, we should enter this while loop. And indeed we do. So the next line, we should set approx to better, and we can see that happens. We update better. And then, because it's a while loop, it's just going to keep executing as long as the condition is true. Now let's take a look at it. Is better equal to approx? No, it's not. So we're going to go execute the while loop. And we can see that as long as this continues to be true at the end of the while loop, we just keep repeating it. And one thing to note here is these numbers, so what Python Tutor is actually displaying, they are just a shorter version of the whole number that the computer is storing. And so even though these look the same to us, inside the computer what's being stored, it has more sort of digits in it. And so at this point, those are all the same. And then finally, we can see that that while loop condition must not be true anymore, and we're going to return the approximation. So Python Tutor shows us the return value, and then that is now this Newton square root of 10 has been evaluated, and so this print statement will happen. And here you can see that there's a lot more digits here, right? So that's why those, even though they looked the same, why we kept going in that while loop. So if I take a look down here at this note here, it says the while statement shown above uses the comparison of two floating point numbers in the condition. Since floating point numbers are themselves approximations of real numbers in mathematics, it is often better to compare for a result that is within some small threshold of the value you are looking for. So what this is talking about is it would be nicer when we're implementing this, instead of going all the way out to two numbers being close, within this many digits, what if we only need equality up to, 100th of integer, 0.01. If they're within 0.01 of each other, we're going to call that approximation good enough. So let's work on updating this code to do that, but as you have probably noticed, you can't edit the code lens. You can see, where things are executed, but you can't edit it. And so what I wanted to do was actually just show you the website that this comes from and copy this in. It's not perfect, but I think it's worth it. So this is the Python Tutor website. You can always paste your code in here if you ever need to. Unfortunately, when I paste from that code lens section, the line numbers are in there, so I'm just going to take a second and delete the line numbers because those would not work. They would not be valid Python statements. But I'm going to try to get my indentation correct here. And then I'm just going to press, I haven't made any changes, I'm just going to go ahead and visualize the execution just to make sure that it's still working. So you can see this is just like we saw in the book. I'm just going to skip ahead to the last, as if we ran the entire program, and you can see we get the same output, so that's great. So the point here was that we can actually go edit this and try out something else. So what we want to do is, instead of continuing to execute this while loop until better is equal to approximate, the approximate answer, we want to only execute while better is within some value of epsilon. Some value of approx. And how do we do that? Well, we can use Python built-in command abs for the absolute value of the difference between approx and is less than some value that we choose. So maybe just so we can really see a difference between this implementation and our last implementation, let's do a sort of large value like 0.1. So now let's go ahead and visualize this. And again, we'll step through. We create our function in the global frame. Now when we go to execute this print function, we need to execute the function itself. And so, well, we can see that I have made an error, which is great. Can anybody spot the error? Well, the error here is that I only enter this while loop. Actually, let's go back to Python Tutor. So here we are. We are about to check condition here, which says the difference between approximation and better is less than 0.1. Well, what's that going to be? It's going to be false. And so we'll never enter this while loop, and we just return immediately. And so how do we fix this? Well, what we wanted was actually for this to be greater, right? So let's go ahead and check that out. Let's get back to the same place we were. So now we're about to check, is this condition true, right? Is approx minus better greater than 0.1? Well, yes, it's 1.5. So we'll go into the while loop, we'll compute our new approx and our new better. Are these within 0.1 of each other? They are not, I would say. Let's take a look. Looks like they're not. And then at this point, are approx and better within 0.1 of each other? Yes, they are. So we will not execute the while loop, and we'll return an approximation of the square root of 10. So that is Python Tutor. Let's go back to our editable code. And so again, I just think this is a really great tool, and I wanted to show it to you.